going on in the Arctic? Is that strong warming in the Arctic related? Is it somehow forcing or contributing to this mid-latitude cooling trend? If you look at the different seasons, winter really stands out. It's very different. You can see the latitude and longitude distribution of the trends. So the top is winter, spring, summer, and fall. But only winter sees this large cooling trend in the continents, and you look at these trend lines on the left. Certainly see since the late 1990s there's been this cooling trend over the whole mid-latitude, which really doesn't show up in the other seasons. There's a very consistent warming trend. But so there's certainly this possible tie, is this really surprisingly unexpected cooling trend in the winter, the Arctic change, Arctic amplification. But the arguments that Arctic is influencing mid-latitude weather is not limited to the winter season, but it extends also to the other seasons. Here's an example for summer. So if you have, the Arctic is warming faster than the rest of the hemisphere, that leads to a decrease in the latitudinal temperature gradient, and a decrease in the latitude temperature gradient is thought to conversely lead to a decrease in the zonal wind and the jet stream. Here's a correlation of jet stream to temperatures, and it's negatively correlated, so that if the wind goes down, if the zonal wind goes down, let's say the weakening of the jet stream, the temperatures go up, and this is especially a strong signal in Europe, even the east coast of the United States, but especially western part of Eurasia. Moscow being a good, this plot here on the right is Moscow, a very good relationship there. But looking at more widely at extremes, looking at precipitation and temperature, so wet, heavy precipitation events and warm temperatures. Shown here a few plots of longitudinal distributions. You can see there's been this increasing trend in total precipitation and very wet precipitation in the number of warm days, and also some time series. And you can see how they've been increasing. Summer months have been increasing, and the wet has also been going up. It also showed some time series for cold temperatures. So overall, if you go back to, say, 1950s in the mid-latitude, there's a generally decrease in the amount of cold extremes. So again, in that interesting period, if you look at that interesting period starting in the late 1990s, there's a trend reversal. So again, not something that was expected. Certainly, based on global warming theory or our expectations and modeling projections, we are expecting increases in heat extremes and precipitation extremes, but not an increase, rather a decrease in cold extremes. But that seems to, at least for the time being, has reversed. Again, this has very important impacts on our society. Here's kind of just looking at trends, all kinds of trends taken from Munich Re, insurance agency, reinsurance agency, and they're also there. What they've been tracking. There's been this very noticeable increase in these extremes, related to meteorological weather events. Has stayed steady as these geophysical, more earthquake events. So, okay, so what could possibly? So we had this over this period of this emergence of Arctic amplification. We've had this increase in extreme weather in mid-latitudes. What are some of the theories that are linking Arctic amplification and mid-latitude weather? I think the one that's the most basic and the easiest to kind of wrap your head around is that if the Arctic is warming faster than the rest of the hemisphere, and of course the Arctic is colder than the equator, that leads to this Arctic amplification leads to a change in the latitude temperature gradient in the sense that it weakens the latitude temperature gradient. That the equator to pole temperature gradient is now weaker because the Arctic is warming. It is experiencing accelerated warming relative to the rest of the hemisphere. But then there have been other ideas, theories saying that changing latitude temperature gradient can change the jet stream. So you weaken the temperature gradient, you also weaken the jet stream, and then this has follow-on or add-on impacts where it changes blocking in the jet stream and wave speed. And then I kind of think of there's kind of been a different set of ideas saying that if the Arctic amplification leads to changes in planetary waves. This has been mostly a winter, idea that's been applied in the winter months. And then for the summer months, it's, I guess, when, the waves get kind of on the smaller scale, but it also changes synoptic waves in the summertime. And then that has impacts on mid-latitude weather and weather extremes. And then maybe one other set of ideas is that that Arctic amplification can change troposphere-stratosphere coupling, which is, again, it's really a winter phenomenon. It's not something that occurs in the summer. But kind of as a caveat, these support of these theories are really conditional on the studies that are being made, and talk about that's in the model, which are both have their inherent imperfections. Now again, some maybe from my talk and my perspective, I think something that is something extremely important about this coupling between Arctic change, Arctic amplification, mid-latitude weather. It can be seen through the polar cap geopotential heights. And so it's just taking the area average of the anomalies in geopotential height poleward of some latitude, chosen latitude. For my plots, I use 60 north. So it's an area average of all the geopotential height anomalies from 60 north to the pole. And you can see in this plot there's a trend starting from the late 1980s. And so you would think Arctic amplification really should be kind of in the lower troposphere, right? So, I mean, if you're melting the sea ice and snow and that warming, I guess at least to first order that should be kind of limited to the lower troposphere. But if you look at the changes in the geopotential height, it's from October 1st to March 31st, and from 1,000 hectopascals up to 10 hectopascals, so into the mid-stratosphere, you can see that the heights have been increasing, almost throughout that entire 6 months and at all levels. It's not just limited to the lower troposphere. And once you get into the free atmosphere, the geopotential heights are a very good proxy for temperature. So not only are you getting throughout the 6 months, like the entire cold season for October through March, this increase in the geopotential heights, but you also get really a warming, and it's something that extends all the way up into the stratosphere, from the surface to the stratosphere, and is very much indicative of more, I'd say, more active stratosphere-troposphere coupling. And if you look at here's an example. If you look at, this is an example from 2012-13. So here on the bottom plot is that polar cap geopotential height against the anomalies from 60 to 90 north. You see throughout that entire warm season, you had this above normal geopotential height, so this warming in the polar cap region. And on the top, just very quickly, is the contribution from sea ice. You can see that a lot of that warming is attributable. People take issue with me if you can't use cause and effect looking at observations, but based on this simple statistic, this is how much of the sea ice anomalies from that season contributed to the warming seen through the winter season. And you can see that you get these kind of pulsating of the polar cap, where the polar cap gets extremely high heights or warm temperatures. And if you look at different extreme events that occur in the mid-latitudes throughout that season, you can see they very nicely match up when you kind of get this pulsating of that polar cap height. So when you get this, this more concentrated or extreme warming of the polar cap, that's when you get have this higher frequency of extreme events in the mid-latitudes. Now jumping on to some, we'll try to focus on the modeling because I know it's a modeling group. And so some experiments looking at low sea ice have been able to simulate things that we've seen in the observations, kind of this connection or relationship, let's say, try to set up between the Arctic change, Arctic amplification, mid-latitude weather. Here's from a recent paper, Kim et al. So they have observations on the left and modeling results on the right. So you can see here in this plot C, and you can look at their polar cap height, and you can see that when they removed the sea ice, they got this warming of the polar cap height, like I just showed in the observations, and something that I've shown for that one particular year 2012-13, where you see the very warm temperatures and the high heights over the Arctic region with colder temperatures in the mid-latitude. So something very similar that I just kind of showed, kind of laid out in the observations. This is the observations on the left, and the model to very good degree simulates what's seen in the observations. It's weaker, but they do simulate that relationship with this warming of the polar cap height and then these colder temperatures in the mid-latitude. That's one modeling. Here's something that came up also again very recently. This wasn't sea ice, but just looking at warming in the Arctic, and depending where the warming was and which side of the Arctic, if it's on the Barents-Kara Sea over here on the left, you got the concentration of cold in Asia, and if it was more on the North Pacific side, maybe the Bering, Beaufort Seas, the warming. Then you got the concentration of cold temperatures were in North America, and here on the bottom two panels, for these two different regions, they show the observations, and then they have the modeling results and CMIP5. To a good degree, the models capture that same relationship where first you have the warming of the Arctic, and then it gets followed by colder temperatures, these cold air outbreaks in the mid-latitude. So again, the models simulate, and again, the top plots here show both the models and the observation. You can see that the model and the observation results overlie each other and are consistent with each other. So again, the model, here's two papers, very recent papers showing that this Arctic warming, this Arctic amplification of the warming is related to colder temperatures, more extreme winter weather in the mid-latitudes. But now getting kind of the caveat part and the big but. First of all, mid-latitude weather is very complicated. There are many things influencing mid-latitude weather, Arctic amplification just being one of them, and you see here we kind of show other forces on mid-latitude weather, and trying to separate exactly, cause and effect is very difficult in the observations. But besides the fact that the mid-latitude weather is very complicated, there's a very short time series, especially if you consider that Arctic amplification has only really emerged in the past 20 years or so. So we have a very short time series. And besides, the problems in the observations, we know of model deficiencies. Modeling studies so far have been uncoordinated. I'll show an example of that in a minute. And just in general, there are biases and uncertainties in all these matrices that we analyze. Still, I would say more and more observational models are coming out that the Arctic change is influencing mid-latitude weather, and certainly, but we'd like to be more definitive about it, and again, maybe showing my own biases where I stand on this issue. But I do think that more studies have been coming out and arguing and demonstrating this relationship, and I think more certainly are coming. Now, talk about this uncoordinated or modeling kind of discrepancies. So here's I got this from James Screen. He was very kind enough to show this, lend this to me for this talk. And this is looking at the mean sea level pressure response to sea ice loss, really focusing on the North Atlantic. A lot of, I didn't really talk about it, it's a very short time that I have, about the relationship with the North Atlantic oscillation and the Arctic oscillation. Much of these colder winters have been associated with this negative trend in the North Atlantic oscillation, Arctic oscillation. So the thinking is that sea ice loss forces a negative North Atlantic oscillation or Arctic oscillation. But if you look at the different modeling results, some models, like this one here on the top left, shows a negative AO, but right beneath it is a positive AO, and you can see in it's neutral AO. And so the models, depending on the model and the center that ran the model, got very conflicting results. So very, very little consistency in the model. So I'd like to try to finish off with one other point, which I think is an important model efficiency, maybe hasn't got as much attention. If you look at the past few winter seasons, if you look at the model forecast, and the NMME site is very good for this, whereas the National Multi-Model Ensemble shows you in real time the seasonal forecast coming out of a whole bunch of models. There are North American and there's international models. But something that's been very consistent in their winter forecast, the models have been too warm. their winter forecast is too warm. Here's a couple of recent examples. Here's from the winter of 2012-13. On the right is the observations, and on the left is the multi-model ensemble. And you can see that it really failed to capture the very cold temperatures across northern Eurasia and in the eastern U.S., where the model is forecasting warm for those same regions. And here's from 2 winters ago, 2013-14. The observations are on the left. Here I've just copied and pasted right off the website. This is the National Multi-Model Ensemble, so these are North American models. Here's on the right is the international models, and it was a very cold winter in North America, but it was also cold in parts of Asia, Central and East Asia, but especially Central Asia. You can see the models are too warm, again, consistently too warm. What the models do get well is this Arctic amplification, this really strong warming in the Arctic. You can see that the models, and you can compare that to the observations, the models do very well, but where it seems to me that warmth that's over the Arctic kind of spreads out into the continent. That doesn't happen in the observations. I think this is important. If you look at, I just regressed a few indices against zonal mean temperatures. Here's the Arctic oscillation here on the top left, sea ice and snow cover. They're all here. You can see that you get this, I think it's a fundamental pattern to the atmosphere, this warm Arctic cold continent, and that Jim Overland has talked about quite a bit. But you get warming in the Arctic, but you get cold temperatures in the mid-latitude. So here's for sea ice, here's for the AO. And here's the modeling results. You can see that hopefully it's clear, but I mean that warming that happens in the Arctic kind of spreads into much lower latitudes in the model than it does in the observations. And here's, again, from that winter of 2014, here's a NASA model, but this is not to pick on one model. So I think this is consistent among all models. So you get that kind of bullseye warming over the Arctic where you have that sea ice loss, but that spreads out, that warmth kind of then spreads out into the interior of the continent. I tend to white out all the temperatures in my temperature plots, but you can see if you look at the observations from that winter compared to the forecast, I mean, you would see that big bullseye as well in the Arctic here. The ocean is massed out, but you clearly see that warming that happens in the Arctic spreads out in the models doesn't happen in the observations. So I think that's a critical model. I think it's somewhat, I haven't determined that is, but I get a strong sense that there's this model deficiency where it's a warm Arctic and a warm continent, maybe not as warm, but it's still a warm continent, whereas there seems to be this dynamical play, interchange between the Arctic and the continents. We have a warm Arctic cold continents that the models don't seem to be capturing at all. I just want to, as Renu mentioned in the introduction, I just want to finish off talking about we've started to look at all of this, Arctic change, and so we have started this working group. The title is, appropriately enough, Arctic change and possible influence on mid-latitude climate and weather, and things that we some of our proposed tasks. We want to try to recommend new observations. Again, the observations are deficient, they're not enough, they're not long enough. How do we overcome those obstacles? But also on the modeling side, we want to kind of, again, there's been this uncoordinated modeling studies. We'd like to recommend some standardized modeling studies. And October 1st, kind of just like a plug here, we're going to have a teleconference, and we have some of the leading scientists, in making modeling studies on an Arctic mid-latitude relationship. They're going to be talking at our next working group teleconference on October 1st. And so, again, another proposed task is to coordinate modeling studies of large ensembles and case studies for identifying physical processes between Arctic change and mid-latitudes, do something, And then we're supposed to coordinate with Arctic groups. So, again, thank you for the invitation. It works out really well with Search, with CLIG, ISC, and IPART, IARP. If I didn't say that so well. And one thing at the end, we're supposed to come out with a synthesis or review project, either a review article. Actually, a lot of the working group members favor special issue. They feel like there's such a spectrum of ideas and on this that one article won't do it justice. And my co-chair is Zhengdong Zhang on this. So just in summary, the past 2 decades, the Arctic has undergone rapid and dramatic change. Strong warming and large variability in sea ice and snow cover could be influencing mid-latitude weather. There's only many theories, studies that argue or show that Arctic variability influences mid-latitude weather through wave interference or jet stream characteristics. But skepticism remains high due to large natural variability, short observational record, inconclusive and ambiguous modeling studies, and modeling deficiencies. And certainly, the need for advance is significant, but I think it's also appreciated by the community, and it certainly seems to me through the working group and through these other groups, efforts are underway to improve the observational and modeling studies. So, thank you very much.
Thank you very much, Judah. This was a nice presentation. It touched on different aspects of what we know and what we don't and how we need to work on it. I'm opening the floor for questions.
I was just like, yeah, so I think everybody had, I know I went through that really quickly, for time, but I think the presentation is available for everybody to, look at your leisure, so.
Mm-hmm. Thank you. Questions from the audience? We've got time for one or two questions, and then we'll move on to the next speaker.
Yeah, this is Jamie Morrison. My question for Judah is, he mentioned the declining AO, and when I look at the AO index for the winters from the NOAA site, it seems like in the early 90s they jumped up, and although they've gone up and down, on average they're still about a standard deviation above what they were before the 1990s. So I guess I'm curious as to what exactly time scale, I guess, that you're talking about.
So again, I apologize I went through that quickly, but when I talk about the negative trend of the AO, it's certainly concomitant or simultaneous with this emergence of Arctic amplification. So, since about 1990, I think, if you did trend analysis of the AO, which I've done many times, I've published and no one's argued with it, the trend is negative, and it's statistically significantly negative. I think if you did the whole time record, maybe, so if you go to the NOAA site, it goes back to 1950, I think you'd see almost no trend whatsoever. There's certainly a lot of papers that came out in the late 1990s, early 2000s say the AO was positive, but that was from the 60s through the late 80s and early 90s. So it's very much dependent on the your beginning and end date of the time series, but from the late 80s or early 90s till now, the trend has been negative.
Yeah, but these processes were active prior to 1990.
Well, what processes are those?
Well, you talked about the strengthening, weakening of the polar vortex. So it seems like
everything I showed about is Arctic amplification and mid-latitude weather is from the late 80s to early 90s. So I would certainly admit that we don't fully understand the interaction, but if you want to, again, I'm just trying to present kind of an overview of what the work has been showing, and if you take so if you really look at that, and one of those early slides I showed that time series, I think it really clearly shows that this emergence of Arctic amplification is from around 1990, the earliest. So I'm really talking since then.
Mm-hmm.
And the sea ice itself really.
I get that too. That it's been declining since 1990, but
right.
It's
so
still.
That's what I'm talking about. And it's another argument. How correct that is to pick that arbitrary date, but if you look at
certainly a big change in the situation.
Yeah. Well, thank you.
Thanks. Any other questions? I'm sure if people have more questions, you can also get in touch with Judah directly. And thank you very much, Judah. This was
You're
great.
Welcome.